Every year, millions of consumers discard the viable genetic core of the modern avocado, completely unaware that this single, heavy seed contains the complete botanical blueprint for a highly productive, multi-decade fruit-bearing tree. The common assumption that domestic propagation from a grocery-bought specimen is a futile endeavor is not a biological fact, but rather a reflection of how modern agricultural systems prioritize uniformity over accessibility. While industrial-scale farming requires absolute predictability in ripening, transportability, and skin thickness, the domestic grower operating on a balcony or a small patio is free from these rigid logistical constraints. By understanding the basic physiological mechanisms of the seed, any patient grower can initiate a developmental cycle that transitions a discarded kitchen byproduct into a robust, structural plant capable of yielding fruit over a multi-decade lifespan. To contextualize why this simple botanical reality is so rarely discussed, one must analyze the history and economics of the modern avocado industry. In 1935, a mail carrier named Rudolph Haas patented a unique seedling in La Habra Heights, California, which possessed an exceptionally rich flavor profile and a durable, pebbled skin that protected the flesh during transit. The global industry rapidly consolidated around this single cultivar, relying on clonal propagation via grafting to ensure that every single Haas avocado sold in modern markets is genetically identical to that original 1935 mother tree. This reliance on vegetative cloning is highly efficient for shippers who require identical ripening windows and predictable physical dimensions. However, this commercial standardization has inadvertently fostered the widespread belief that growing a tree from a seed is an impractical, failed strategy, conflating commercial uniformity with biological viability. From a botanical perspective, the assertion that seed-grown avocado trees are incapable of producing fruit is inaccurate. While it is true that a sexually propagated tree, one grown from a seed, will exhibit genetic variability and will not be an exact clone of its parent, it remains fully capable of flowering and fruiting once it passes its juvenile phase. The resulting fruit is a unique genetic individual, often possessing excellent culinary qualities, even if its skin texture or ripening speed varies slightly from the standardized supermarket standard. For the home horticulturist, this genetic diversity is not a defect, but an engaging element of natural variation. While nursery grafted saplings offer a shorter path to maturity at a significant financial cost, seed propagation represents a low barrier, highly educational entry point into long-term perennial cultivation. At the center of this process is the seed itself, which is often mistakenly treated as inert waste. In biological terms, the avocado pit is a single, highly developed seed containing two large cotyledons that store nutrients, and a central embryo composed of meristematic tissue, active, undifferentiated cells capable of developing into roots, stems, and leaves. Surrounding this delicate structure is the testa, or seed coat, a thin, paper-like protective barrier. Many novice growers make the mistake of scrubbing or peeling this layer away, exposing the sensitive cotyledons to fungal pathogens and mechanical damage. Preserving this protective envelope is the first critical step in ensuring the embryo wakes from dormancy in a stable, disease-free environment. Initiating germination requires careful handling of a fresh seed, ideally within 24 hours of extraction when viability is highest. After gently rinsing the pit to remove any remaining fruit pulp, it is critical to leave the protective brown seed coat completely intact to shield the embryo from pathogens. Successful development depends entirely on identifying the seed's biological polarity. The slightly flattened, rougher end constitutes the basal region from which the primary root or radical, will emerge, while the more pointed end is the apical region that produces the shoot. Misidentifying these ends is one of the most common reasons germination attempts fail, as the embryo cannot establish proper vascular orientation if suspended upside down. To facilitate root development before transplanting, a simple water suspension setup is highly effective. Inserting 3 wooden toothpicks at a slight downward angle around the midpoint of the seed allows it to rest securely on the rim of a glass vessel. The vessel is then filled with room temperature filtered water until only the bottom third of the seed is submerged, placing the setup in a warm environment with bright, indirect light, ideally maintained between 65 and 75 degrees Fahrenheit, provides the necessary thermal cues to break dormancy, to prevent oxygen depletion and discourage opportunistic bacterial growth. The water must be replaced entirely every 5 days, maintaining a clean medium for the emerging root system. The transition from a dormant seed to a developing seedling occurs over a structured, multi-week timeline. Between weeks 2 and 6, the seed will split along its natural seam, a physical indicator that the internal tissues are expanding. By week 10, a single primary taproot typically emerges and extends downward, followed closely by the upward growth of the shoot between weeks 10 and 14. Once the central stem reaches approximately 6 inches in height, a critical intervention is required, pruning the stem back by half. This action temporarily disrupts apical dominance, the hormonal control exerted by the terminal bud that suppresses lateral growth. By removing this top growth, you interrupt the downward flow of auxin, forcing the plant to activate dormant lateral buds and produce a branched, sturdier trunk structure rather than a fragile, singular stalk. Following this initial pruning, the seedling develops a more complex root architecture and secondary foliage around month 4 to 6. Once the root system is robust and the new lateral branches have stabilized, the plant must be transitioned from water to soil. The primary hazard during this transplanting phase is root hypoxia, or wet feet, caused by poorly drained, compacted soil. To ensure adequate aeration, the seedling should be potted into a 1-gallon container using a highly permeable substrate mix, consisting of 70% standard potting soil and 30% coarse horticultural sand or perlite. This mixture permits rapid moisture drainage while preserving necessary hydration, setting a foundation for the tree to reach a height of 18 to 24 inches by the end of its first year. Growing an avocado tree in a container introduces specific physiological advantages that can accelerate the transition to fruiting. Unlike in-ground trees, which prioritize expansive vegetative growth and deep root systems for many years, container-bound trees experience a phenomenon known as root restriction, when the root system encounters the physical boundaries of a pot. Hormonal signals prompt the plant to shift its metabolic energy from structural expansion to reproductive maturity. To sustain a tree in a container long-term, such as a 7-gallon pot, periodic root pruning is necessary. Every 2 years, the tree is temporarily removed from its vessel so the outer third of the fibrous root mass can be trimmed, allowing the plant to be repotted with fresh substrate in the same container without becoming dangerously root-bound. The secondary challenge of container cultivation is securing successful pollination. Due to the unique flowering behavior of Persea americana, avocado flowers exhibit synchronous complementary dichogamy, acting as functionally female during one part of the day and functionally male during another. To overcome this barrier to self-pollination, cultivating 2 separate seedlings in close proximity is highly effective, because each seed-grown tree is a genetically distinct individual. Their daily flowering cycles often exhibit slight variations in timing. Having two trees blooming side by side increases the likelihood of pollen transfer during overlapping male and female phases, significantly improving the overall fruit set in a residential environment. An advanced botanical optimization involves the targeted application of salicylic acid during the early stage of germination. Salicylic acid is an endogenous plant hormone that regulates growth, development, and systemic acquired resistance, the plant's internal defense mechanism against pathogens. Introducing a minute dose of this compound during the second week of water suspension, using a quarter of a crushed, uncoated aspirin tablet, acts as a mild physiological stress stimulant. This exogenous signal prompts the waking embryo to allocate more resources toward building a denser, highly branched root system. This early structural reinforcement significantly enhances nutrient uptake and mitigates transplant shock when a young sapling eventually transitions into soil. Ultimately, successful seed propagation requires an understanding of genetic heterozygosity. Because Persea americana is highly heterozygous, its offspring will display a unique combination of traits rather than replicating the exact characteristics of the parent tree. While a commercially grafted tree offers a shorter juvenile phase, typically fruiting within 2 to 3 years, a seed-grown tree represents a longer commitment of 4 to 7 years. However, this extended timeline costs virtually nothing and bypasses the chemical dependencies of industrial nurseries. By working with the plant's natural developmental phases, home growers can successfully cultivate resilient, long-lived perennials that contribute to domestic food security and promote genetic diversity.